The dream of achieving an electric car that can travel 1,000 miles on a single charge has always seemed almost mythical. For decades, automakers and researchers envisioned a future where range anxiety was a relic of the past. Yet, technical limitations, particularly in battery chemistry, kept this dream on the horizon rather than in reality. Now, however, that horizon seems closer than ever, thanks to the groundbreaking work of CATL, the world's largest battery manufacturer and longtime Tesla partner. Their new lithium metal battery has crossed the threshold of 500 kg, an unprecedented leap beyond current technologies. Compared to Tesla's widely used 4680 battery cells, which operate at around 272 kg, this achievement nearly doubles the energy density. Even more impressively, it surpasses the most advanced solid-state batteries, which average about 375 kg. This difference might sound like numbers on paper, but in practical terms, it means a revolution in mobility. A car that once traveled 300 miles could now reach close to 1,000 miles without increasing the size or weight of its battery pack. It is nothing short of a transformative moment for the industry. At the core of this breakthrough lies a radical shift in chemistry. Instead of the traditional graphite anode, CATL engineers have implemented pure lithium metal. This substitution may seem like a material swap, but it represents a profound redesign of the cell itself. Lithium metal allows for a far higher density of stored ions, resulting in batteries that are lighter, smaller, and vastly more efficient. The implications ripple through design, performance, and cost in ways that extend far beyond simple numbers. The promise of such batteries reshapes not only how far cars can drive, but also how they are conceived. Smaller packs mean vehicles can be designed with sleeker bodies, lighter frames, and improved aerodynamics. Performance gains become more achievable without sacrificing comfort or safety. In essence, cars can become more dynamic and versatile while still delivering record-breaking range. For the first time, electric vehicles stand poised to exceed the travel distances of many gasoline-powered cars with ease. One of the most significant psychological barriers to EV adoption has been range anxiety. Potential buyers often hesitate, concerned about being stranded without access to charging. The CATL lithium metal breakthrough eliminates that fear almost entirely. With a 1,000-mile range, even long cross-country journeys become feasible with minimal stops. The driver's mindset changes from constant planning around charging stations to enjoying the freedom once taken for granted in traditional combustion cars. This isn't just about convenience for drivers, it's also about infrastructure. A vehicle with triple the range of today's models drastically reduces the need for frequent charging stations. Instead of building dense networks of chargers to accommodate limited ranges, urban planners and companies can strategically place fewer stations. This reduces cost, energy strain on grids, and accelerates the rollout of electric mobility in regions previously hesitant due to infrastructure challenges. Of course, achieving this leap was not the result of sudden luck. It represents over a decade of sustained research, investment, and bold experimentation. CATL dedicated enormous resources to understanding and refining lithium metal chemistry, something that had eluded commercial viability for years due to stability and safety challenges. Their persistence and collaboration with Tesla created a synergy that allowed this technology to leave the laboratory and edge closer to reality. Despite the breakthrough, durability remains a significant obstacle. Current prototypes demonstrate approximately 483 charge cycles, less than half of what conventional lithium-ion batteries can deliver. While this is a limitation, it's one that CATL is attacking with sophisticated methods. Advanced artificial intelligence is now being deployed to analyze cell behavior, predict degradation, and propose new chemical configurations to extend battery life significantly in future iterations. The central issue in durability lies with the electrolyte, the component that facilitates the flow of ions within the cell. In lithium metal batteries, the electrolyte tends to degrade faster, limiting overall cycle life. By applying AI-driven modeling, CATL aims to stabilize these electrolytes and unlock the full potential of the chemistry. The challenge is immense, but the payoff could redefine not only electric vehicles but also energy storage across industries. Parallel to their work on lithium metal batteries, CATL has also pushed forward on another promising technology, sodium-based batteries. One of their most notable developments, the Naxtra battery, represents a different branch of innovation aimed at affordability and resilience. With an energy density of 175 Wh/kg, it may not match the range-extending capability of lithium metal, but its other features make it revolutionary in a different way. The Naxtra sodium battery boasts a staggering 10,000 charge cycles, ensuring longevity far beyond conventional batteries. This alone changes the economics of ownership, as fewer replacements mean lower long-term costs for consumers. Equally impressive is its ultra-fast charging capability, allowing a vehicle to recover 500 kilometers of range in just 5 minutes. For drivers, this means a quick coffee stop could be enough to keep going for hours. Another crucial advantage of sodium-based technology is its thermal stability. Unlike lithium, sodium cells can operate safely across extreme temperatures, from frigid 40°C winters to scorching 70°C summers. This robustness opens markets in regions where lithium-ion struggles, such as extremely cold or hot climates. It also enhances overall safety, reducing the risk of thermal runaway and fires even in severe accidents. Sodium also addresses a growing concern: cost. Lithium and associated materials like cobalt and nickel are expensive and subject to volatile global markets. Sodium, on the other hand, is abundant and inexpensive. By replacing costly materials with sodium and aluminum, the Naxtra battery cuts costs by as much as 30%. This democratizes EV ownership, bringing electric mobility within reach of a far larger audience. The CATL-Tesla partnership ensures these breakthroughs won't remain confined to research papers or small-scale prototypes. Tesla, with its global manufacturing reach and market dominance, can integrate and deploy these innovations into production vehicles at scale. Early reports suggest that the first cars equipped with lithium metal batteries could appear within the next 2 to 3 years, marking a historic milestone in automotive progress. The implications stretch far beyond passenger cars. With lithium metal batteries, Tesla could revolutionize trucking, buses, and even aviation. Long-haul trucks could travel routes previously impossible for electric power without constant recharging. Electric buses could serve entire metropolitan regions on a single overnight charge. Aircraft powered by these batteries could redefine sustainable aviation, offering quieter, cleaner, and longer-range flights. The blend of lithium metal and sodium battery technologies creates a portfolio of solutions suited to different markets. Premium, long-range vehicles could adopt lithium metal packs, while affordable models designed for mass adoption could rely on sodium. This tiered strategy ensures that electric mobility can expand at every price point, meeting both high-performance and budget-conscious demands without compromise. Beyond the direct consumer benefits, the environmental impact is profound. Longer-lasting batteries reduce waste, as fewer replacements are required over a vehicle's lifespan. The use of sodium further diminishes reliance on rare, environmentally taxing resources like cobalt. Together, these advances lower the ecological footprint of EVs, aligning with global sustainability goals. The economic implications are equally significant. Cheaper, more durable batteries drive down the total cost of ownership, making EVs not only desirable, but also economically practical. Businesses, fleets, and logistics companies stand to save substantially on fuel and maintenance. Governments, too, benefit from reduced emissions and infrastructure costs, accelerating policy adoption and subsidies. Tesla's role in this transformation is pivotal. As a leader in electric mobility, Tesla has the capability to push these innovations into mainstream consciousness. Whether through the next-generation roadster, semi-trucks with unheard-of range, or affordable models equipped with sodium packs, Tesla's ability to commercialize ensures that these breakthroughs reach millions, not just a privileged few. As with any new technology, skepticism remains. Critics question the scalability of lithium metal batteries, their long-term stability, and whether promises can match mass-market realities. Yet history shows that transformative technologies often begin with limitations before iterative improvements make them viable. The very fact that prototypes now exist at such high energy densities is evidence that the tipping point is near. In parallel, sodium batteries may face skepticism about range limitations compared to lithium. However, their low cost, high safety, and ultra-fast charging capabilities position them as ideal solutions for urban and mid-range applications. For many consumers, affordability and convenience outweigh the allure of extreme range, especially as charging infrastructure continues to expand. Artificial intelligence will play an increasingly central role in this story. CATL's use of AI to analyze chemical combinations accelerates research cycles dramatically. Instead of relying solely on years of trial and error, AI can simulate millions of possibilities, guiding researchers toward the most promising solutions. This fusion of data and chemistry embodies the next era of technological acceleration. Looking at the broader market, these developments place pressure on competitors. Companies investing in solid-state or traditional lithium-ion technologies may find themselves outpaced if CATL and Tesla succeed in scaling production. This competition is likely to ignite a new wave of innovation across the industry, benefiting consumers and accelerating the global shift to electrification. Governments and regulators will also play a decisive role in shaping this landscape. Policies supporting cleaner technologies and renewable integration will gain traction as more robust and affordable batteries hit the market. Countries seeking energy independence will see sodium batteries as a strategic advantage due to their reliance on abundant materials, reducing geopolitical dependencies tied to lithium supply. The public perception of EVs could shift dramatically. For years, critics pointed to limitations in range, charging time, and battery cost as reasons to doubt electric mobility. With these hurdles being dismantled simultaneously, the narrative changes. Electric vehicles no longer represent compromise but rather superiority in range, efficiency, safety, and cost. The appeal broadens from enthusiasts to the general public. For Tesla specifically, this positions the company at the forefront of a new industrial revolution. While competitors scramble to keep pace, Tesla's early adoption of CATL's innovations ensures they maintain their leadership. The introduction of 1,000-mile vehicles or mass-market sodium-powered cars would not only disrupt the auto sector, but ripple into energy, logistics, and aviation. This transformation also extends to renewable energy storage. Grid-scale batteries using sodium could stabilize power supplies, store excess renewable energy, and reduce reliance on fossil fuels. Lithium metal, with its high density, could enable portable solutions for industries requiring extreme energy efficiency. Together, they redefine how societies store and distribute power. Consumers stand to benefit most from these changes. Vehicles that last longer, cost less, charge faster, and drive farther fulfill nearly every desire of the modern driver. Beyond cars, buses, and trucks, even personal devices and home storage solutions could adopt versions of these technologies, creating an interconnected ecosystem powered by advanced batteries. The democratization of technology is one of the most exciting aspects. By slashing costs with sodium chemistry, EVs become accessible to families and individuals once priced out of the market. What was once a luxury becomes mainstream, driving adoption at unprecedented rates. This inclusivity ensures that the electric revolution is not limited to wealthy markets, but expands globally. As infrastructure adapts, the charging experience itself transforms. Ultra-fast charging capabilities mean that long waits become unnecessary. For many drivers, the experience will feel more convenient than gasoline refueling, as cars gain hundreds of miles in the time it takes to enjoy a short break. This change directly challenges the last psychological barriers holding some consumers back. Sustainability lies at the heart of these innovations. By embracing abundant resources like sodium and extending battery lifespans, the environmental burden of EV production decreases significantly. Recycling efforts also become more manageable, as sodium cells avoid the toxic and rare materials that complicate traditional battery disposal. This creates a cleaner cycle from production to end of life. The impact on global emissions could be transformative. As transportation accounts for a large portion of carbon emissions, the mass adoption of cleaner, longer-range EVs directly contributes to climate goals. With affordable sodium options and ultra-dense lithium metal solutions, both urban and long-haul sectors can decarbonize simultaneously, accelerating progress toward a greener planet. Markets like aviation and shipping, often seen as untouchable by electrification, suddenly have pathways forward. The density of lithium metal makes it feasible to power aircraft for regional routes, while sodium could support short-haul maritime transport. These applications extend the scope of electrification far beyond personal cars, making entire industries cleaner and more efficient. In the near term, the rollout of these batteries will reshape consumer choice. Buyers will weigh factors like extreme range versus affordability, but no longer will they face the compromises of the past. Each option, Whether a sodium-powered urban compact or a lithium metal long-range luxury model will outperform today's best offerings. It's a consumer-driven revolution where choice, not limitation, defines the market. The automotive design language will evolve as well. Freed from the bulk and weight of oversized battery packs, designers can rethink vehicle proportions, interiors, and performance profiles. Cars can become sleeker, lighter, and more efficient without sacrificing safety. This new freedom marks the beginning of an exciting chapter in automotive aesthetics and engineering. Energy companies, too, must adapt. The combination of fast charging capabilities and higher capacity packs will require upgraded grid management and expanded renewable integration. Yet, with better storage solutions, grids will become more resilient and capable of handling surges in demand. This symbiotic growth benefits not just EVs but the entire energy ecosystem. Fleet operators stand to gain some of the most immediate benefits. Delivery companies, ride-sharing services, and logistics providers rely on cost efficiency and reliability. Sodium batteries promise lower costs and durability, while lithium metal enables extended routes without downtime. These advantages improve profitability while reducing environmental impact, aligning business with sustainability. Public transportation will also see a renaissance. Electric buses running on advanced batteries can deliver consistent service with minimal charging interruptions. Cities benefit from cleaner air, reduced noise pollution, and lower operational costs. The shift makes public transit more attractive, reliable, and environmentally friendly, supporting broader sustainability goals. Education and workforce development will play roles in this revolution. As new chemistries and manufacturing processes scale, skilled workers will be needed to design, produce, and maintain these systems. This creates opportunities for job growth across sectors, from research and engineering to manufacturing and recycling, spurring economic development alongside environmental benefits. The ripple effects reach geopolitics as well. Nations that embrace sodium-based batteries reduce reliance on lithium-rich regions, redistributing global power dynamics in the resource economy. This shift could ease tensions while fostering new trade relationships centered on abundant, evenly distributed elements like sodium and aluminum. Consumers will likely respond positively as awareness grows. The narrative of an affordable EV that charges in minutes, lasts decades, and runs safely in all conditions is compelling. Combined with premium offerings that redefine range expectations, the market appeal spans demographics, geographies, and income levels. This is how revolutions truly spread, by meeting everyone's needs at once. The potential for aviation deserves emphasis. Electric aircraft equipped with lithium metal batteries could drastically cut carbon emissions in regional travel. These planes would be quieter, safer, and less polluting, revolutionizing short-haul flights. While challenges remain, the pathway is clearer than ever before, and the implications for sustainable aviation are monumental.